Okay, welcome everyone to Robotics 1. In today's class, I'm going to talk about inverse kinematics. Please note that we are kind of change the sequence in a sense that the DH parameters will be discussed later in the class. I just want to go with the flow, the way the textbook is going. So in the last class, we talked about how to do the inverse kinematics. And to do the inverse kinematics, what we need to do is we need to write down the kinematic equations and then try to solve the kinematic equations. So just give me a minute here. My Apple Pencil for some reason is not working. So let me get this set up. So in the last class, we talked about a very simple inverse kinematics problem. In that inverse kinematics problem, we just had a simple 1 degree of freedom robot. And that 1 degree of freedom robot, we worked out the inverse kinematics. Okay. So let me explain the concept behind inverse kinematics. Inverse kinematics is very important when you are interested in robot doing particular task. Say for an example, you want robot to go from point A to point B. So consider that you have an articulated robot. Articulated robot means robot with hinges. So if you have a robot, something like this, you have the first revolute joint, okay, well, so you have this end effector, and what I want to do is I want this end effector to go from point A to point B. So I want this end effector to go from point A to point B. The only way this end effector can follow this prescribed movement is by changing the joint angles. So these are the joint angles theta 1 and theta 2. So the question is, what should be the combinations of theta 1, theta 2 at time t is equal to 0? What should be the values of theta 1, theta 2 at time t is equal to 0.1? What should be the values of theta 1 and theta 2 at time t is equal to 0.2? Only then Once we know these values of theta 1 and theta 2, so that the end effector position, say for an example, this is the first position at time t is equal to 0. This is the second position at time t is equal to 0.1. This is the third position at time t is equal to 0.3. What I want is I want to find out the values of theta 1, theta 2 for different instances of time so that the end effector can track the trajectory from point A to point B. And then this could be a very simple operation like painting. So imagine that robot has a paintbrush and we want this robot to paint, or this robot has a spray gun and we want to spray something. So we need to know the inverse kinematic solution so that the robot can follow the trajectory from point A to point B. So let's try to identify this problem in a step-by-step fashion. So the problem is, if this robot is drawn in the configuration that I have shown, and for the first case, let me just take the example of a planar robot. So I have this robot. This is theta 1, and I have this another robot arm. This is link 1. I'm gonna call this link 1, link 2, and this angle is theta 2. And this is the end effector position, which is Px and Py. Now, one thing I want you to note, which is not very clear, that this theta 1 and theta 2 are both with respect to the datum, which means if you consider this horizontal line x and you have this vertical line y, they represent the coordinate system of the 0th frame. You have theta 1 and you have theta 2. Now, if Px is given to us, this distance is Px, this distance is Py. So given the value of Px and Py, so the inverse kinematic problem can be written as, given Px and Py, find theta 1 and theta 2. So what I'm going to do is, I'm going to find out the expression in terms of theta 1 and theta 2. So check this out. So first and foremost, let me draw horizontal and vertical lines. This distance is L1 cosine theta 1. This distance is L2 cosine theta 2. This distance is L1 sine theta 1. And this distance is L2 sine theta 2. So what it means, my equations are of the form L1 cosine theta 1 plus L2 cosine theta 2 is equal to Px, L1 sine theta 1 plus L2 sine theta 2 is equal to Py. Now, check this out. What I have is I have two equations and I have two unknowns. So my equation number one is relating cosine theta 1, cosine theta 2 with px. My second equation is relating sine theta 1 and sine theta 2 with py. So in theory, I have two equations and two unknowns. My unknowns are theta 1 and theta 2. So I should be able to solve this equation. But unfortunately, the problem is not that simple. And I want you to take a minute to think about how this problem could potentially be solved. Because even though the unknowns are theta 1 and theta 2, the angles are given in their cosines and sines form. The angles are not given to us in their direct form. So if you decide to solve this equation directly, trust me, you will go in circles and you will never reach the answer. And the reason for that is because these are transcendental functions. These are sines and cosines. They will get expressed in each other term. So I'm going to tell you two tricks. And remember these tricks very carefully. So these are the classical ways the inverse problem can be solved. So trick one. If you have an equation, something like this, let's take an example of the same equation. L1 cosine theta 1 plus L2 cosine theta 2 is equal to Px. And the second equation is L1 sine theta 1 plus L2 sine theta 2 is equal to Py. Let's understand L1, L2, Px and Py are known. So L1, L2, Px and Py are known. So what I'm going to do is, check this out. I'm going to identify the same transcendental terms. So see here, this is L1 cosine theta and this is L1 sine theta. One rule I know, that sine square theta 1 plus cosine square theta 1 is equal to 1. So what I'm going to do is, I'm going to take L1 cosine theta 1 on one side. I will have Px minus L2 cosine theta 2 on other side. Same thing, and just for clarification, let me show here what we are doing. For the same thing, I'm going to have L1 sine theta 1 is equal to Py minus L2 sine theta 2. I'm going to square both sides. So when I square both sides, I will get L1 square cosine square theta 1 is equal to Px minus L2 cosine theta 2 square. Here, same thing, L1 sine theta 1 square. So this will become L1 square sine theta 1 square is equal to Py minus L2 sine theta 2 square. Now I have these two equations. What I'm going to do is, and I want you to focus on these equations for a minute. I'm going to call these equations equation 1 and equation 2. If I add equation 1 and 2, equation 1 plus equation 2. If I add equation 1 and equation 2, I would get L1 square cosine theta 1 square plus L1 square sine theta 1 square is equal to Px minus L2 cosine theta 2 square plus Py minus L2 sine theta 2 square. Now L1 can be taken outside, L1 square. So you have cosine square theta 1 plus sine square theta 1. And on the right hand side, you are going to have a quite long expression. But let's write that expression for a second. So it's going to be Px square minus 2 times Px L2 cosine theta 2 plus L2 square cosine theta 2 square plus Py minus 2 Py to Py L2 sine theta 2 plus L2 square sine square theta 2. This guy, please note, is equal to 1. So on the left hand side, I just have L1 square, and L1 square is known. So this guy is known. On the right hand side, I have Px square. Please note, Px square is also known. I have minus 2 Px L2 cosine theta 2. Then I have plus L2 square cosine square theta 2 plus Py square minus 2 Py L2 sine theta 2 plus L2 square sine theta 2 square. Now let's identify out of these terms which terms are completely known. L1 square is known, Px square is known. Please note, this guy is known. C cosine of theta 2 is not known, but it should be 2 times Px L2. L2 square is known. Py square is known. 2 Py L2 is known, and L2 square is known. Observe here, I have L2 square cosine square theta. I have L2 square sine square theta. So I can combine these two terms together, and I'm going to use the space down below. So this will become yeah, L2 square cosine square theta 2 plus sine square theta 2. So this guy becomes 1. So what you have L1 square on the left hand side, then you have bunch of knowns on the right hand side. The only quantity at this point is not known, and that I'm going to highlight. The quantity that is not known is cosine theta 2 and sine theta 2. So everybody with me so far? So right now what we did, we started with the coupled equations, and now we landed up with only one equation that has sine and cosine terms. And I'm gonna rewrite this equation into the most general form. And believe me that most of the times you are gonna have the equation that is something like this. Once again, let me repeat. The highlighted terms, the blue highlighted terms are constants. So these guys are now known. So the only unknowns are cosine theta 2 and sine theta 2, which means I'm gonna write this equation 3 in the most general form. And typically at the end of solving inverse kinematics problem, you are gonna have an expression in this most general form. So equation 3 is of the form. Equation 3 is of the form something like say c square is equal to some term a cosine theta 1 plus some term b sine theta 1, or let me just say c is equal to a plus b, where c, a and b are known and only unknowns are only unknown is at this point theta 1. So we have to solve this expression. Now let me ask you a very simple case. There are two cases that are possible. Say case 1. Case 1. Say somehow some magic happens and then I know c is equal to 0. So somehow the numbers work out in such a way that your value of c happens to be 0. Then what you land up with is you have 0 is equal to a cosine theta 1 plus b sine theta 1. This expression can be written as minus a cosine theta 1 is equal to b sine theta 1. So what you can do, and you can clearly see from the expression, this expression is of the form a divided by b is equal to tan theta 1. Now it is very tempting to say theta 1 is equal to tan inverse of minus a by b. It is very tempting. So, but here is the issue with the tan function. What? Okay. Okay. So you have, so I just, to be consistent, is theta 1. Okay. So now what you have is, you have a tan inverse, but tan function does not work in all 4 quadrants. And please understand that the robot could have more than one solution, or the robot could have solutions that are in two different quadrants. And let me give you an example. Say this is my endpoint, and my robot could be configured something like this. So I could have my first joint, I could have my second joint, and my end effector would reach this position. Or I could have my first joint oriented like this, I could have my second joint oriented like this, and still I am able to reach the end effector position. But if you were to use the tan inverse function, it will just give you the solution in the first quadrant. So the function to use in robotics is called arctan, arctan, which is arc tangent. And the MATLAB command for arctan is a tan 2, and you would have y comma x, and it should be parentheses. So I should, if I want to find out theta 1, in this case, I should be using the command a tan 2. My y is a, so minus a comma b. And this will give you the correct orientation of theta. It will tell you where, in what quadrant theta lies. Everyone understood this? Now let me discuss case 2, which is more interesting and slightly convoluted. So before I go to case 2, I just want to make sure that everyone understood how to solve this problem. Any questions? Okay. Now, the other thing is this the only way to find theta 1? And the answer is no. There is one more trick that you can do. And please pay attention. And why all these tricks are needed? Because as I said, there are two solutions of theta 1. Theta 1 could be this, and theta 1 could equally be this. So we want our solution to be consistent, and we want to find out all the possible solutions, not just one solution, but all the possible solutions. So here is trick 2. Again, case A, case 1, trick 2. So now the equation that I have to solve is of the form minus a cosine theta 1 is equal to b sine theta 1. Okay. So what I'm going to do is I'm going to square both sides. So I need to write this down here. This is method 1. And this is method 2. So a cosine theta 1 is equal to b sine theta 1. I'm going to square both sides. So when I square both sides, I would have a square cosine square theta 1 is equal to b square sine square theta 1. Now, this allows me to use a famous identity. And that famous identity is sine square theta 1 plus cosine square theta 1 is equal to 1. So cosine square theta 1 plus sine square theta 1 is equal to 1. So what I could do now is I could replace a square cosine square theta can now be replaced with 1 minus sine square theta 1 is equal to b square sine square theta 1. So now what has happened is I have replaced sine square term, cosine square term with a sine square term. And now, as you can see, this entire expression is only in terms of sine square theta 1. So this expression can now be rewritten as a square minus a square sine square theta 1 is equal to b square sine square theta 1. And I'm gonna go outside the slide here a minute. So this equation now becomes a square is equal to a square plus b square sine square theta 1. In other words, I have, and I want to be very clear, sine square theta 1 is equal to a square divided by a square plus b square. Now, some of you may ask me, what does this mean? And this equation, even though it's not very clear at this point, I want you to notice that this is a quadratic equation, which means this equation has two solutions. Sine theta 1 is equal to square root of a square divided by a plus b, a square b square plus, and sine theta 1 is equal to minus square root of a square divided by a square plus b square, which means now you have two solutions to angle theta 1. And if a's and b's, the geometry works out, then you will get two solutions. So you will get two values of theta. So please note, you are gonna get theta 1, 1, and you are gonna get theta 1, 2. Everybody understood this? So these are two methods to solve this equation. But again, please note, this is case 1. There is one more case, and that is actually important. So before I discuss case 2, everybody understood that if you have an expression where you have just sine and just cosine of one angle, it could be theta 1 or it could be theta 2, but not theta 1 and theta 2. Everything should be in just one angle. Then you can use method 1 or method 2 to find all the solutions. Now, next thing is case 2. So case 2 is very important. In case 2, you have, let's go with the same equation, C is equal to A cosine theta 1 plus B sine theta 1. But C is not equal to 0. Now, what happens then? In that case, once again, there are multiple methods, and I'll show you both the methods. So what you can do is you can do C square, and then you are going to have the right hand side of this equation can be written as a square cosine square theta 1. So a square cosine square theta 1 plus 2ab sine theta 1 cosine theta 1 plus b sine square theta 1. B square sine square theta 1. Now please note, if A and B are same, and you want to be very careful about it, so sometimes you will see A is equal to 5 and B is equal to -5. That case will work too. You will see A is equal to 5, B is equal to 5. That case will work too, which means if you have a condition A square is equal to B square, A square is equal to B square, these two terms can now be combined. So this guy and this guy can be combined. So you can combine these two terms. If A square is equal to B square, you land up with an equation C square is equal to 2A square, A square cosine square theta 1 plus sine square theta 1 plus 2AB cosine theta 1 sine theta 1. This term is now 1. And out of that, C square is known, A square is known, 2AB is known. So we are left with cosine theta 1 and sine theta 1. What should we do now? So check this out. In this case, we have to use a substitution. And remember this substitution, this is a trig substitution. So what we are doing is trigonometric jugglery, nothing else. So cosine theta 1 is equal to 1 minus tan theta 1 by 2 divided by 1 plus tan theta 1 by 2. Sine theta 1 is equal to 2 tan theta 1 by 2 divided by 1 plus tan square theta 1 by 2. So what I need to do now is I will have to substitute C square is equal to A square plus 2AB, and cosine theta, this term is going to become 1 minus tan square theta 1 by 2 divided by 1 plus tan square theta 1 by 2, and then this gets multiplied with 2 tan theta 1 by 2 divided by 1 plus tan square theta 1 by 2. Now please try to understand, we started with a simple equation and now this equation has become super complex. So but here is at the end going to happen, and I want you to follow this equation. Once all multiplication is done, you will land up with a nice quadratic equation that can be solved by the formula minus b plus minus square root of b square minus 4ac divided by 2a. So at this point, you want to multiply and carry out the multiplication. And this is a thought exercise that I just want you to do. So check this out. So tan square theta 1 by 2 multiplied by 1 minus 1 plus tan square theta 1 by 2 gets multiplied. And this term gets multiplied with c. So you are going to have 1 plus tan square theta 1 by 2 square is equal to a square plus 2ab, and then you are going to have 2 tan theta 1 by 2 minus 2 tan cube theta 1 by 2. And then once you expand this equation, you are going to have a fourth order equation. For that, the formula or the solutions are readily known. And some books use this approach, and many a times what they do is they use some sort of numerical technique or MATLAB or Newton-Raphson to solve the problem. But what I want to do is, I want to give you a simpler way of solving this equation. And this is like slightly a simpler way. So check this out. So the equation that we are trying to solve is C is equal to A cosine theta 1 plus B sine theta 1. Instead of trying to simplify this equation any further, what I'm going to do is, at this point itself, I'm going to replace cosine theta 1 is equal to 1 minus tan square theta 1 by 2, 1 plus tan square theta 1 by 2, and sine theta 1 is equal to 2 tan theta by 2 theta 1 by 2 divided by 1 plus tan square theta 1 by 2. And then this equation becomes A multiplied by 1 minus tan square theta 1 by 2, 1 plus tan square theta 1 by 2 plus B 2 tan theta 1 by 2 divided by 1 plus tan square theta 1 by 2. I'm going to multiply left side and right side by 1 plus tan square theta 1 by 2. So my equation now becomes 1 plus tan square theta 1 by 2 is equal to A in the parentheses 1 minus tan square theta 1 by 2 plus B 2 tan theta 1 by 2. And whether, I don't know if you can notice this, this is a simple quadratic equation. So this equation, I can make a substitution, something like tan theta 1 by 2 is equal to u, and then I have c 1 plus u square is equal to a 1 minus u square plus b 2u. Expanding this, I have c plus cu square is equal to A minus AU square plus 2BU. This equation can be easily written as, on the left hand side, I have a big 0. This equation is going to be U square minus A minus C plus 2B U plus A. So this is a simple quadratic equation wherein this is A, this is B, this C. So U is equal to minus B plus minus square root of B square minus 4AC divided by 2A. And what it means is you are going to have two solutions. You will have U1, so tan theta 1 is equal to U1, and you will have tan theta 1 is equal to, I'm going to call U11 and U12, and theta 11 and theta 12. You will have two roots, two solutions. So remember these tricks. These tricks are super duper handy when we are trying to solve a complex problem. So where did C go? A, B, C. Oh, so this is small c. So I'm gonna call C, B, A. So B, C. So A minus, so C is here. This capital C is different than the small c. So this C and the small c, C square, oh, yeah, you're right. Yeah, you're right. So correct. I missed one minus C square. So did I do it right? A, okay. Yeah. A minus C square. Which one? Oh. Okay, I see what you're saying. This is A minus C. Okay, are we good? Yeah, okay. So this C is here. And this C goes here. Okay, so some of you may think, hey, this is too much mathematical jugglery, but believe it, we have to go through all this to find the solution to the inverse kinematics problem. And sometimes if you are using MATLAB, you may be able to solve transcendental equations with sines and cosines with numerical techniques. And I would encourage you to take a look at it. And now I'm going to solve a big inverse kinematics problem. I don't know if I would be able to finish it, but I will try. And then what I will do is I will try to use MATLAB to work out some of the math. So so maybe I will run out of, we will go over time, but let's finish this inverse kinematics problem, because this is not a spectator sport. So these techniques or these tricks that we talked about that are used in finding inverse kinematics. So you need to be familiar with this. But one thing I want you to remember, that this substitution always helps. So wherever possible, try to convert the equation into this form and then make the substitution. The previous technique that I showed you may be more suitable for a numerical analysis when you have a MATLAB code or you have a numerical technique that can solve the equation. But if you are interested in finding out answers by hand calculations, then this substitution would always help. But I need to give you a side note, and just please remember this side note. Sometimes, so this is side note. Sometimes you will have an equation which is of the form of C is equal to A cosine theta 1 plus B sine theta 1 plus D cosine theta 1 multiplied by sine theta 1. So you may have a solution, or you may land up with an equation which is of this form, wherein you have A cosine theta 1, B multiplied by sine theta 1, and D multiplied by sine and cosine theta 1. In that case too, this substitution works. So if you have an equation of this form, the substitution works. So try to make it as simple as possible, and just make sure that only one variable, theta 1 or theta 2 is present. You can't use these tricks if theta 1, theta 2, theta 3 are present. But in this, just make sure that you just have theta 1, theta 2 or theta 3, and then you can actually use this trick. All right. So I'm going to start this big inverse kinematics problem. So everyone, please pay attention. Imagine that we have an articulated robot, and this robot is made up with 3 revolute joints. So you have this first revolute joint, you have this second revolute joint, and then you have this third revolute joint. So this is an R robot, where the first R is parallel to the second R is parallel to third R. So you have R parallel to R parallel to R robot. And what I want to do is, I want to find out the inverse kinematic solution. This is my end effector. So the position of the end effector will be known. And since this is a spatial robot, which means this is a 3-dimensional robot, you will have Px, Py, and Pz. And perhaps you will have some orientations too. So how would you solve an inverse kinematics problem with 3 revolute joints? The first step in solving an inverse kinematic problem is to solve forward kinematics problem. So let's solve the forward kinematics problem by assigning, this is going to be my Z0, this is going to be my Z1, this is going to be Z2, and this is going to be Z3. Then let's add x's. This is going to be x0, and remember we have to follow the rules. So x1 has to be perpendicular to Z1 and Z0. So this is X1, and then this is going to be X2, and this is going to be X3. Then we need to add our Y's. So I have Y1, I have Y2, and then I have Y3. So this is Y0, this is Y1, Y2, and Y3. Are you with me so far? So we have drawn the coordinate systems. Let me give you some lengths. So this length is A1, this length is L1, this length is A2, this L2, this A3, this distance is L3. So we have A's and L's, and A's and L's are constant except the distance, the joints. If you had some non-zero rotation, the L1s would rotate. So this is going to be theta 1, this is going to be theta 2, this is going to be theta 3. So I have theta 1, theta 2, and theta 3. This is my 0th frame, first frame, second frame, and third frame. Are you with me so far? Any questions regarding the setting of the frames? Now, one key observation here is, fortunately for me, frame 1 or frame 0 is aligned with frame 1, frame 2, and frame 3. So fortunately for this particular problem, frame 1 is aligned with frame 2 and frame 3. What does this mean? It means the projection matrices are all identity. Projection matrices are identity. As frame 0, if you remember the procedure, what we have to do is, first we need to have the rotation matrix, and I will just do it for one joint. So first we need to have the rotation matrix, so 0 R1, and since the rotation is about Z, I have cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1 multiplied by the projection matrix, and this projection matrix is x0, y0, z0, x1, y1, z1. Please note, x1 is aligned with x0, y1 is aligned with y0, z1 is aligned with z0. So this matrix is actually identity, which means when I multiply 0R1, what I'm gonna get is 0R1. So what it means is I can take a shortcut and I can write the homogeneous transformation matrices fairly quickly. And I want you to follow the way I'm writing the homogeneous transformation matrix. And I'm going to take a shortcut, but if you don't follow, just send me a message in the chat window and I will work out the problem step by step. So first, I'm going to have 0h1. 0h1 will look like cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Then I will have 0, 0, 0, and I will have 1 over here. Then I need the distances along x0, y0, z0. Distance along x0, and note x0 is this, distance along x0 and distance along y0 has to be valid for all the values of theta. So this is going to be L1 cosine theta 1, L1 sine theta 1, and this distance about z is going to be A1. Are you with me so far? Now please note 1h2 can also be written as cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1, 0, 0, 0, and now here I need the distances along x1, y1, z1. So the distance along x1 is going to be L2 cosine theta 2, L2 sine theta 2, and I have A2. Are you with me so far? And this homogeneous transformation matrix, strangely enough, looks similar to the homogeneous transformation matrix 0h1, except theta 1 is replaced by theta 2, L1 is replaced by L2, and A1 is replaced by A2. Moving on, now I have 2h3. And can someone tell me how would the matrix look like? Come on, follow the trend. Cosine theta 3 minus sine theta 3, sine theta 3, cosine theta 3, 0, 0, 0, 0, 1, 0, 0, 0, 1. And here I'm going to have L3 cosine theta 3, L3 sine theta 3, and A3. And please note, this was possible because these joints were identical to each other. So this is a simple manipulator, and in case if you are wondering how does this manipulator look like, this manipulator looks something like this. Then if this is the motor, on this motor you have a link. There is another motor, and on this motor there is this link, and there is another motor, and on this motor you have this link. So you have your first revolute joint, and let me show you just the Z's, your second revolute joint, and your third revolute joint. So you have R, R, and R. And that is how this robot is going to look like. Everyone clear about how this robot is going to look physically? Now what I want you to do is, I want everyone to look from top. And can you see that this robot is exactly similar to the robot that I have drawn here, except it has 3 links, which means if I were to draw this robot something like this, then this robot, which is the spatial robot, is going to look similar to the planar robot that I have drawn over here. Now, as you can see that to solve this planar robot, we had to go through a lot of jugglery. So what do we need to do to solve this robot joint? And I'm gonna use MATLAB in this case. So bear with me, I'm going to switch screens and then I will show you how this problem would be attempted in MATLAB. But before I proceed further, if you have MATLAB or if you have a laptop with MATLAB, please start the MATLAB and then follow the way I am working out the problem. Okay. Can you see my MATLAB screen? Okay. So I'm gonna start a new script. Inverse kinematics problem. And I'm going to have following symbolic variables. My symbolic variables will be T1, so SYMS, T1, this is theta 1, T2, this is theta 2, T3, this is theta 3, A1, A2, A3. Then I will have L1, L2, L3. So these are my symbolic variables. H01 will be my first homogeneous transformation matrix, cosine T1 minus sine T1, 0, L1 cosine T1. Then I'm gonna have sine T1, then I will have cosine T1, then I will have 0, no, L sine 0, and then I will have L1 times sine T1. Then I will have 0, 0, 0, 0, 1, 0, 0, okay, 0, 0, 0, 1, 0, 0, 0, 1. Actually, it will be 0, 0, 1, A1, 0, 0, 1, A1, and then last 0, 0, 0, 1. Okay, what I'm gonna do is, just for my own satisfaction, I'm gonna run this, and just to make sure that I have typed my homogeneous transformation matrix correctly. Now, all of you, just check if I have inputted my homogeneous transformation matrix correctly. So first 3 by 3 is the orientation matrix. Last vector is the distance between the 0th frame and the first frame. And I think it looks correct. So I'm going to take a shortcut. I'm going to say copy this, copy. Then I would paste and just replace T1s by T2. L1s by L2s. And A1 by A2s. So now I have H0, 2. And I'm going to repeat the same process, copy. And then I'm going to go to the next step, paste, H0, 3. Same drill, cosine theta 3, sine theta 3, L2, L3, T3, T3, L3, T3, A3. Okay, does my matrix, the H1, 0, 1, 0, 2, 0, 3, they look okay to you? So H0, actually I made a mistake. This should be 1, 2, and this should be 2, 3. Nobody caught it? I'm surprised. H03 is equal to H01 multiplied by H12 multiplied by H23. Everyone with me so far? And I am going to run this code. Wow. Now I got this large expression. So in this expression, I have, if you look at the last column, this is where all my positions are. So what I'm going to do is I'm going to highlight this for a second. I have L1, L2, L3, all this big expression. I'm going to copy this and I'm going to say simplify. Paste. Wow. After simplification, do you notice that this expression got reduced to something super simple? Now I'm going to take the second expression. Copy. And then I'm going to try to simplify this too. So I would say simplify. And then I'm going to paste. Enter. Wow. So my expression got simplified. And if you look at the last element, which is just A1 plus A2 plus A3. What this tells me is, let's assume Px, Py, and Pz are the coordinates of end effector. So which means I give you Px is equal to 10, Py is equal to 10, Pz is equal to 10. I have a neat and clean expression for Px, Py, and Pz. So my Px is gonna look like, my Px will be copy, then here paste.
Copy again, so it will not paste anymore.
Py copy, paste, and Pz is equal to A1 plus A2 plus A3. So solving the inverse kinematics problem means, so I need to write this down here. Solving inverse kinematics problem means for given Px, Py, and Pz, find T1, T2, and T3. Now, one thing I want you to note, which is important here, that A1, A2, A3 is constant. So Pz must be constant. Because what it means is A1 cannot be changed, A2 cannot be changed. So the only thing that you can change is Px and Py. You cannot change Pz. Pz will be fixed. Okay. Now the question is, how do we solve this problem? And so you can do simplify H03. That should be fine too. Now, one thing I want you to note, that depending upon how the problem is set up, there are some tricks that you can play. And so for an example, sometimes if the angles are given to you, then you can actually use those angles. So let me show you what I mean by that. It probably is not clear. If I do simplify H03, check this out, that big matrix gets converted into a simple matrix. Now I want everyone to look at the terms that I highlight. Having an inverse problem, which means we have this matrix, but we know on the right hand side, we have the final positions and perhaps we have final orientations. which means we know what is cosine T1, T2, T3 is. We know what is the sine T1, T2, T3 is. We know what is this value. We know what is this value, because recognize that first 3 rows and first 3 columns, they are the orientations of the end effector. So assuming that this guy is known, you can substitute its value over here. Assuming this guy is known, you can, or this guy is known, you can substitute its value over here. And then finally you land up with the equation that is comprising of T1 and T2. And once you have T1 and T2, then you will do the same mathematical jugglery that we did for the robot arm to find the solutions of the problem. So what I'm going to do here is I'm going to stop here because I'm 10 minutes out of time. So we will stop here, but I will go ahead and discuss, continue discussing this problem on Monday. So in the meanwhile, if you have any questions, I would be happy to answer. I'm going to stop recording.